Yes? I don't hear it echoing. Testing? Oh, that's better. Now I can really annoy you. Nobody sleeps today. Okay. So the point is the Erlangian family allows us to solve these. But the problem with them is that every one of them, every distribution in that family, has a coefficient of variation which was, in fact, less than 1, which means it's less random than the exponential, because the exponential has coefficient of variation, which is 1. So that's not quite as general as we like. So we said, let's introduce another approach, parallel servers, which looks like this. Instead of putting stages in series, we'll put them in parallel, and thereby go into a parallel sequence, which gives us this service time density. And sure enough, that family allows us to go above 1. So now we've, in some sense, completed the range. You just have to pick which HR you want. These are called HRs, hyperexponentials. And in fact, we said, let's go a little further. Let's even take a family like this, but make it not just a single stage, but multiple stages in series, as in particular in this example. So we have basically capital R chains, each chain of length R sub I, and each service stage of value Ri mu I. And in fact, we could do even more than that. We could change the rate for each of these as well. So we have an enormous amount of generality, at least with an approach. We said we could do more than that. By the way, this particular case has that service time density transformed. We said there's another approach by Cox, which allows us to do it as follows. You have this is the service facility. Customer comes in, makes a choice. Either he leaves immediately, or with probability beta 1, he goes into a stage mu 1, tosses a different coin, probably alpha 2, he leaves, or continues on. So he goes, takes one of these paths, and that particular density has a transform that looks like this, quite general. And in fact, all of these, as you can see, lead to rational functions of the density. I mean, these are basically powers of S. No logarithms, no exponentials, simply polynomials in S. And it turns out you can approximate any non-rational density with a rational sequence such as this, get fairly close to it. Now, what that's going to do, of course, if you try to calculate what's going on with say a Coxian as the service time, and suppose you had an arrival stage like that and a Coxian service stage, you got to keep track in which state you're in, which stage of arrival, which stage of service, and how many are in the queue, and that's at least 3-dimensional. So you can write down the equations. How do you write them down? Inspection. Trivially. You have to be careful, make sure you don't miss any unusual states. You write down a set of linear difference equations. How do you solve them? Z transform. Can you, in fact, get a clean solution for P of Z, the Z transform? Probably not. But at least it's an approach, and you could try to find roots if you like, etc. Or, as I pointed out, because this is a large set of linear difference equations, throw it at a computer, let it solve it numerically. Not a very comfortable solution, but an approach, which means we can actually solve, as I mentioned last time, all GG1 systems by using these families as basically airline generated. Oh, by the way, this Coxian gives us no more generality than these systems up here. But there's many different approaches to get to them. So we could, in principle, using Erlang's wonderful intuition, solve all GG1 systems numerically, as closely as you like. But we're going to do better than that. We're going to find analytic solutions for many of these systems without having to resort to numerical computations. So what I want to do now is that's the end of the review. What I want to do now is go into something called networks of Markovian queues. Now the important idea, it's a network, which means there's more than one queuing station. The example that one can use is you're machining say the case for this computer. The first thing you have to do is you have to stamp out the base in a stamping machine. Then you may have to attach the top piece. Then you may have to insert a piece of the printed circuit board. And then you may have to put in a memory of some sort. In each case, you want to first stamp it out. You go to a system which does stamping. You're the stamper. I join a queue of other parts waiting to be stamped. And after they finish being stamped, they go on to the guy who's going to attach the top. Another queuing system. Then another queuing system, in fact, to insert the printed circuit board. So you're bouncing around in a physical network, each one of which is a little queuing system. And the question is, how do these networks of queuing systems behave? Now, I actually addressed some of this in my very first lecture. I pointed out where queuing theory lives. Queuing theory lives in a single node, typically. You have an arrival process, some kind of queuing system, a service process, and you leave how long you spend in that system. But I also pointed out you could have a network of systems, as I'm starting to describe, where in fact all of the distributions are deterministic. The service time in this stage is exactly 3 seconds, and the arrivals are coming in exactly every 4 seconds. And when they leave here, they go to another one with fixed constants. So they're moving around in this network. So it's purely deterministic, but the complexity comes from the structure of the network and the questions you ask. For example, supposing the rate at which this station pumps things out is 10 per second, and yours is 3 per second, and yours is 1.5 per second, and yours is 100 per second. Well, if I want to go through that sequence and pop out there, what's the rate at which I can come through the system? What's the throughput of the system? And what's the maximum capacity that we can handle? And so that involves a whole field of theory that we're not discussing. It's called, anybody? Yes? Excuse me? You're talking about operations research. It's in that general field, as is queuing theory, but this particular technology is called network flow theory. It's networks with everything deterministic. You know how large everything is, how fast they come, but they're going through a complex network. And the question is, what's the maximum kind of flow from this node to that node through this complex network? It may be passing through this guy who's going at a very slow rate. It's better to go through 3 other nodes going at a faster rate. So what's the maximum throughput you can get? Or what's the cheapest route to get through? Or how reliable is the system? Questions of that sort are very sophisticated. There's a whole field of theory that we're not working on called network flow theory. And it's fairly sophisticated. And the way it gets a little more complex is, suppose we're not just sending computer parts through here, we're also sending herds of cattle through here. Suppose it's a railroad system, okay? You're sending computers and cattle and oil, all in the same freight car. The question is, how many cattle per day, computers per day, and barrels of oil per day can I get through? It's a multi-commodity, 3 commodities in that case. The multi-commodity network flow problem is unsolved. You can solve it exactly for 2 commodities. More, it's computationally very complex. Oops, tough field. Now, on the other hand, queuing theory with a single node, if it's deterministic, is very easy. If it's stochastic, that's what we're spending this whole quarter studying. But what if we had a network of stochastic queues? Now you got the network flow problems, and by the way, it's multi-commodity if I start sending messages through this, and you've got the stochastic issues. Horrible problem. We really can't solve that combination at all. So what do? We'll talk about that in a little while. But right now, I want to talk about the case where we're studying only networks of Markovian queues. It means we're going to have a network of queues And the questions we're going to ask are the usual questions. How many people at different locations? Oh, he tells me I've got to connect up this little baby here again. Okay. So we're not going to do network flow theory. We're going to do networks of flows. Now, let me give you a very simple example of a Markovian queue. Suppose this is station number 1, and this is station number 2. And what they represent are queuing systems. These are not states of a queuing node. This might be the, you come into a system and you get your parts manufactured, and here you come into another system and you get it painted, okay? Each one consists of a queue, a server, and some arrivals. And let's make this rather simple. Let's assume that things come in to the first node. They pass through the first node, then they go to the second node, and then they leave. That's basically a two-node queuing network. And let's assume that things are clean. For us, clean means Poisson arrivals, okay? We know a lot about them. And suppose these are even exponential servers, say at a rate mu for each, okay? Now, how do you solve this system, okay? This is what we call a two-node tandem network. Okay, so what's interesting about this? For example, can you solve this system? Yes. What is it in our queuing terminology? M for Poisson arrivals, M for service, single server. We assume it's first come. We know how to solve that thing. It's MM1. Boom. But you look at the second node now. What's the arrival process for the second node? In words, or some description. What's feeding the second node? Output from the first node. So the inter-departure time from the first node is the inter-arrival time to the second node. And if it's exponential, maybe we can solve it. Well, so we have to find what is the inter-departure time for an MM1 system. We haven't talked about that, have we? So let's begin to talk about it, okay? I'm going to let me make this black. Let's define D of t as the PDF of the inter-departure time. From node 1. Again, I want to emphasize this. Picture you're looking at is not a state diagram. It's a network picture. It has two nodes, okay? And I'm going to define d star of s be the Laplace transform of that density. Okay. So let's figure it out. Now, when someone leaves node 1, how long for the next guy to leave? Well, there's two cases when he leaves. Either he leaves an empty system, or he leaves a busy system. And let's break those two out, okay? So, if he leaves, say, a non-empty system, busy system, namely, in that case, what will d star of s be given non-empty on departure? Anybody? That's not a function of t, which we're looking for, or s. Okay, physically, guy leaves. Somebody immediately goes into service in node 1. How long before that person leaves? Because that time is the time between two arrivals to the second node. How long does he spend in the first node? It's a service time. So if you will, it's b star of s, whatever that b star is. If it's exponential, that's one thing. Otherwise, it's this. Okay? Let's look at d star of s given he leaves behind an empty system. Well, let's think about it. You leave, you arrive at the second node. Now, the first node doesn't get busy until what happens? Somebody arrives to the first node. Then that guy goes right into service, and we have to wait till he finishes service. And some of those 2 times is the time for the inter-arrival time, inter-departure time, if you will. Okay, how long for a Poisson arrival for the next guy to arrive? What's the Laplace transform of the inter-departure, of the inter-arrival time to node 1? In words or mathematics? That's the density, and what if it's Poisson, the A is exponential, and its transform is lambda over s plus lambda, right? That's a Laplace transform of the time for the guy to arrive at node 1. Remember, it's memoryless. Doesn't matter what else was happening, okay? And then we have to add to that an independent random variable, which is the service time in the first node. And what's that? That's b star of s, right? I haven't said it's exponential yet. I will in a moment, okay? Now, let's choose b star of s. Let's assume service time is exponential at rate mu. Then what is b star of s? Anybody? Everybody? Come on. Of course, mu over s plus mu. That is the transform of the density of an exponential at a rate mu. Okay? So let's get the, and by the way, what's the probability that a departure leaves behind an empty system? We're going to need that. It's an MM1 system. What's the probability that a departure leaves behind an empty system? What's the fraction of time an MM1 system is empty? With some notation.
1 minus lambda over mu.
Exactly. 1 minus lambda over mu, which is 1 minus rho, right? That's P0 for MM1. Okay, let me just say that's P0. Okay, so we want d star of s now, and that's equal to these two conditions multiplied by their condition, okay? So with probability 1 minus rho, the system is empty, and then we're going to have an inter-departure time, d star of s, given system empty on departure of the first guy, plus the opposite, probability rho, d star of s, given non-empty. But we just cooked those two terms up, so let's write it down. That's it, it's 1 minus rho. What's d star of s? It's empty. That's this function up here. We just cooked it up. It's lambda over s plus mu, lambda over s plus lambda. Times mu over s plus mu. Or probability rho, what's d star given it's not empty? That's just this function here, namely mu over s plus mu. Oops. That's rho times mu over s plus mu. Okay. Now, you can do the algebra as well as I can. I'll leave that to not even a homework assignment. This turns out to be lambda over s plus lambda. Simplifies very nicely. So, d of t is an exponential at a rate lambda. It's exponential. Since lambda of s plus lambda has inverse lambda e to the minus lambda t, namely same as the inter-arrival time. Very nice. So now we've understood a piece of the problem. The arrival rate or density to node 2 is lambda e to the minus lambda t. That's the inter-arrival time for 2 or inter-departure time from 1. That's very nice. That means I can string these babies together and keep getting exponential inter-departure times. Okay. So this leads to something called Burke's theorem. Whoops. And it says the following. Poisson in to an MM1 system to an MM1, in fact, sequence leads to inter-departure times which are exponential. Now, I'm using shorthand notation for that. It's really a little more sophisticated. But the point is the output process, I'll write that in parentheses here, the output process, namely the inter-departure time, is independent. Burke showed that. We haven't shown that here. Of all other processes in the system. And more than that, MM1 is the only first come first served system with this property. So that's pretty neat. You string together a bunch of Poisson arrival to an exponential server, that feeds another exponential server, feeds another exponential server. That chain is such that the inter-departure time between any pair of nodes is exponential at the same rate as the arrival process, and it's independent. So every node looks like an independent MM1 system. So you want the joint distribution of how many in the whole system? K1 in node 1, K2 in node 2, K3 in node 3. If they all had the same mu, then it would just be basically the probability raised to the number of nodes power. If they had different exponential times, you just take a product of each of those MM1. Pk it would be 1 minus rho to the k, where the rho depends upon the surface rate. You can write it down immediately. They're independent, so it's a product of probabilities. Okay. Now, I'm going to generalize the topology suddenly. I'm going to create something called a Jackson network. And this is a lovely piece of architecture. Let's draw a structure not of a series, but let's draw a bunch of nodes or stations by which you travel. So let's create a node 1, a node 2, a node 3, a 4, a 5, a 6, etc. Any arbitrary structure you want to draw. And let's assume that when you leave node 1, you go to node 2 with some probability, or maybe you go to node 3 with some probability, but that's all. And from node 2, you may go to 5, you may go to 4, and from 3, you may go to 4, and maybe to 6, and 4, you may go to 5. I'm making all of this up. And probably, possibly, maybe to a final node here. Let me call it 7. Okay. Now, with what probability do you move between nodes I and j? So I'm going to indicate the probability going from node 2 to node 5 is r sub 2, 5. Namely, r sub ij equals the probability node j next given node I now. And let's assume each node, let's say the ith node, has, let's say, m sub I exponential servers. So it's not a single server node, but has multiple servers. Say m sub I exponential servers. So I'm making this fairly general. At rate mu sub I. So each node has a number of servers. Each server is an exponential. And each rate for different nodes is different. Okay. So we know what Rij is. And by the way, of course, Rij is greater than or equal to 0. There's no negative probabilities here. Okay. Now, after, so everybody got the structure? You jump around, pop, 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 pop. You may return to a previous node, etc. Okay. Okay, so now after node I, the customer can leave the system. By system, I mean network. Let me be explicit about that. With probability equal to 1 minus probability going anywhere else, okay? Equal to 1 minus the summation over all other nodes, j equals 1, say, to n nodes, of r sub ij. So this is called an open network because you can leave. And by the way, I have yet to talk about the arrival rates. Let me put that back in this picture. Say to a particular node I, there's an external arrival rate of customers. And let me call that gamma, in this case gamma 5, in general gamma j. I want to get notation. I'm going to call it gamma I for the ith node. Gamma I is the external arrival rate to node I, and we're going to assume it's Poisson. And let's give it a rate. I just gave you the rate. It's gamma sub I. Well, there it is. It's the rate. So now we have a complete system. Things come in from outside. They hop around, and eventually they leave. Okay. Now, what would you like to find? What, I mean, here's a system. What questions might you ask about it? Well, one obvious question is, what is the actual rate going into a given node? It's got the external and the internal. So let's write that out, okay? Let's say lambda sub I is the total arrival rate to node I. And what is it? It is equal to, well, the external, gamma I, that comes in from outside, plus stuff comes in for any other node. So let's figure that out. Summed over all other nodes, j equals 1 to n. There's n nodes in the system, I'm assuming. How much comes from node j to me? I'm node I. How much comes to node 5 from inside? Something comes from 2 and something comes from 4. How much comes from 2? Excuse me? R25 times what? That's the R25 is a rate. By the way, this is an R. I want to write it more carefully, not a gamma. That's an R25. Whatever 2 has as its input rate, R25 if it goes to 5. So what I need here is the amount that j has, which is lambda j yet to be found, times the rate, the probability of going from j to I. This is good for all I from 1, 2, up to n. N is number of nodes. I haven't specified that, but I've said it. And it turns out we'll be able to learn that this system is ergodic if no node gets overwhelmed, which means if its input rate, lambda I, is less than its service rate. And what's the service rate of node I? Mu I if there's only one server, but there's m sub I servers. Where are they? It's somewhere here. Oh, here, right here. So it's, what is it? It's mu I times m sub I. That's the rate at which you can pump people out. They better not come in any faster than I can pump them out, or else the rho for that node would be 1 or more, and it will blow up. So that's the stability condition, okay? Good. You'd like this for a homework problem? I'll give you a particular, yes? Yes, yes, you can allow RI. That's why I didn't exclude, in this sum, I did not exclude j equals I. Absolutely, you can return. Good question. Okay. Yes?
You wrote this formula as a general rate formula, but the network is not every node gets flow from 2 other nodes.
Then the RJI would be 0 for that pair. Notice, if you believe this picture, R35 is 0. There's only an R25. Oops. And there's an, here, an R45. But there's no R35. So it's 0. And that would appear as a 0 in here. So it's all taken care of. It's perfect. And this, by the way, what I just wrote down, you could write down for any kind of network. I don't need Poisson. I don't need exponential. This is flow in equals flow out, okay? Because what is lambda I? Lambda I is what you're pulling in and therefore taking out. Okay. Now, what would you like to solve for this? Well, the thing I've been bothering you with all these weeks is to find the probability of so many people in the system. Usually the system is one node, P sub k. Now I'd like to ask that for every node. What's P1, pk2, pk3? What's the P sub 1, comma 2, comma 3, comma up to n? What's that joint distribution of people in the system? Looks like it's hard to get. But suppose I actually ask you to do that, maybe this baby example. How would you approach it? And I'll tell you it's Poisson in and exponential service. How would you approach it, Matt? Right. Right. Matt knows the answer all the time. This little puppet here, I can. Come on, okay, you're right. I shouldn't say that. Smart guy. Designated smart guy. So by inspection means you write down the very complicated state description. Namely, if you say there's so many in the system at node 1, node 2, blah, 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 where can you go from having K1 in node 1, K2 in node 2, K3 in node 3, up to Kn in node n? Where can you go? Well, what can happen? What's the next event? I'll tell you right now, there's so many in each node. What can happen next to change that? What goes on in this network? People come in, and people move between nodes, and people leave. So, for example, if I give you the state at a given point in time, one thing that can happen is there could be an external arrival to this node that moves you to another state where node number 1 has increased by 1. Well, wow. Or someone could have left this way, in which case I have to go to another case where node 1 dropped down by 1, node 2 dropped up by 1. Now you can imagine how complicated this state diagram is. It's multidimensional, one for each node. But you could write it down if you really had to. You could write down pk1, comma k2, blah, blah, kn, times its arrival rate and service rate and balance flow. And you get a very complicated set of linear difference equations. Now, Z-transform is not going to help you. It's just too complicated. Can you think of another way to try to find the answer? What's true of ergodic queuing systems, or ergodic systems? The pi j's or the pj's are unique. There's only one answer. So the trick is guess the solution. Plug it into your complicated equations, and if the equations are satisfied, you got it. So Jackson said, I'm going to try that. And guess what he attempted to do? I mean, if you had to guess in the next 10 minutes, what would you assume? Well, the only thing we know pretty much now is exponential. So assume that each node behaves, like Burke said, an independent MM1 system with the input flow that we got from this equation over here. We know what the traffic is on the ith node. You can solve this. Assume it's an MM1 or an MM sub I system. We know the answer from chapter 3. Plug it in, and son of a gun, it solved the equations. Brilliant move on his part. He got the answer. So let me write that down as, guess what? Jackson's theorem. Okay. And by the way, James Jackson, was a professor here at UCLA, and he published this thing in 1957 in the Journal of Operations Research. Okay. Let me first write down what it says. He said basically that the probability of finding K1 in node 1, K2 in node 2, out to K sub n in node n is equal to probability of finding K1 in a one-node network, call it P1, times P2 of K2, I'm going to explain what these are in a moment, out through P sub n of Kn, where P sub I of K sub I is equal to the solution to a plain old M sub I queuing system with the appropriate input lambda sub I. It's a product solution. And it looks as though each node is behaving as if it's an isolated M sub I node with the traffic we just calculated from this equation up here. I keep pointing to it. With that lambda I. So given the gammas, that's an external input, we know that number, and given the RJIs, and given the mu's, we can solve for P sub I of Ki. Given all that, we can find lambda. Once you got lambda I, it's a plain old M sub I system with input lambda I, service rate mu I with M sub I of them. Bang, go back to chapter 3 and you got the equation. Beautiful. So I'm going to say that this is a product form for Markovian Qs. Now, a couple of comments. One, personal comment. I started doing my research on computer networks in 1959, 1960, and I saw this paper. Because it was the only, what was the problem I was trying to solve? A computer network, nodes, links between them, traffic coming in, bouncing around, and leaving. Namely, the internet kind of thing. And how does it behave? Well, it doesn't quite obey the model I described here. And the reason it doesn't obey that is because it fails the Burke condition, which means that the inter-arrival times are exponential. And the reason that's the case is because the way we got this here is because the time here and the time here and the time to come in were all independent random variables. In a computer network, that's false. And it leads to a set of equations which are basically impossible to solve. I was able to show how difficult that is in general. And 19 years later, a wonderful queuing theorist named Boxma, who was a student of J. Cohen in Holland, solved a two-node case with equal capacities between those nodes. Took him 20, and it wasn't an explicit solution. It was basically an iterative solution. The problem is still unsolved. So my God, here I am. I'm a doctoral student, and I got my problem. Can't solve the damn thing. What do? You're going to face that, those of you in graduate school. Got a model. It's the right model. Boy, if you can solve this, you really have done something. So what would you do? The mathematics fails. I got a whole chapter about that. It leads to terribly complex Laplace transform equations and difference equations. Okay, what do you do? Go home and cry? Or there's actually three things you can do. One, build it and measure it and see the way it performs. Well, that's billions of dollars and years later. That's not a good answer. Come on, what's another thing you can do today with big computers? Okay, approximate is the third answer. I was going to suggest simulate the damn thing. That you could do. You guys are all great programmers. Simulate it. Bang. Measure it. Third, as John says, approximate. Bring in an approximation which lets you use a solution. So my approximation was simply, I'm just probably off. Oh, it's on again. Good. Approximation was that, yes, this is an independent. Namely that as you travel through each node, you randomly choose the service time, which is what this model says. It's false in the network. So you make that approximation and bang, the problem falls apart. Jackson's theorem gives you. Then there's a lot more to do. How much capacity to use, what kind of routing, what kind of control, and all the rest. But the basic problem is solved. But what's one more step you have to do if you throw in an approximation to get the solution? you have to prove the approximation is good. Two ways to do that. Build it. Oh my God. I found that with the approximation and without the approximation, the answers were almost identical. Bang, done. And then but that was a kind of greater. So Jackson's work was beautiful. It wasn't meant to apply to the case where there is dependency, but you can approximate and get a good solution. Okay. So that's fact one. Fact two. Jackson was wrong. Each node in his network appears to behave like an independent MMI system, okay? It appears to behave that way. The mathematics shows it does, but it does not behave that way. That's false. But the mathematics turns out to be the same. You don't have to solve the complicated problem. And he was able to show that, which is brilliant. Okay, so let me just make that point, because I don't want you to go away thinking this is a correct interpretation. The nodes are not. Get rid of this ruler somehow. Yeah. Okay. So the point is, I'll say it's amazing because the nodes are not independent. M sub I. But the mathematics makes it look that way. Okay. So I want you to chew on that a lot. I've tried to bother you with a few things today, namely a very complicated problem, and as researchers, what you do with a hard problem. You know, what are your approaches? What can you do? What should you assume? Okay, let's take a break. We'll start in 10 minutes. Want me to put this here? It'll be easier for you. Yeah. It'll be louder for you too. Yeah. You want me to take care of that?
The what? The homework?
Yeah. You want to?
I had a quick question on the midterm.
Sure. I sent the solutions around, by the way.
Yeah, I did. I saw that.
Okay,
Yeah.
good.
Is that a 75 or a 76?
5.
Huh?
5.
75. Okay.
Yes.
All right. Then
You can check that I did the addition correct.
Yeah, the addition adds up to 75.
Okay.
But then I have one issue here. The 1 point that you've deducted here on
Yes. Okay.
question 5.
Let's look.
You've given me -1 here for this problem, and you've like crossed it out and written the exact same term I have, 1 over 2 minus p.
Let's see. Let me-
So why do I have a point deducted?
maybe a mistake. Let's see.
Like what you've written in red and what I have in black is the exact
Let's
same.
check the solutions,
Okay.
okay? Disconnect this.
Yeah, I don't remember what the
Okay.
matrix was off the top of my
It's
head.
okay, we'll go find it. Let's look at the solutions. There it is. Okay, and that was which problem
La-
1?
Problem 5, the very last one,
Okay.
third from last
Sure.
part.
It seems it needs, it's a 2 over 1 minus p. Let's go to the end, okay? There's p to the end, okay?
Yeah, p to the end.
Well, up here.
So 1,
Let's look at this, okay?
let's see
1 minus p, 1 over 1 minus,
well,
2
that's the
minus
other-
p. This is correct.
see
So,
one-
maybe I made a mistake. Okay. Don't know why I said that. By the way, this should be little piece of n, right?
Yeah, I mean, I
Right,
just,
right, right.
I,
No,
I
no,
just,
no, no, that's my fault.
That's fine. I just went
Yeah.
with what I had on the midterm.
Okay,
so-
I don't know why I took that off. I'll give you the point, sure.
Okay.
Okay. Um,
So that should be a 20. That
That's
should be a
it.
30.
Yes, let's make that a 30, okay.
And then wait, before you go there, I
Oh,
want to
okay.
ask
Y-
about
yeah,
another one.
okay,
So that you can just make the final correction on
sure,
this one.
okay.
For problem 4 here, at least, I don't know if I'm doing math wrong, but like I don't have any issues with what you've deducted here. But if you add it up, minus 6, minus 10, that's minus 16, minus 17 and a half, minus 19.
Okay,
So if I have minus 19 here, shouldn't that be a 16?
okay, maybe let's, where is,
But this was crossed out work. We're not
Excuse me?
considering this.
who crossed it out?
Me.
That's, you wrote that in
No,
red?
no. I
Oh.
crossed out my work
Oh,
because
so-
I was wrong.
So where is it?
So it starts here.
Oh, okay.
So
Oh,
Like
and
I
I didn't sell you that? I guess not.
no.
Okay.
No, you told me like I did ask you about this.
Oh,
on the
I
exam.
checked it? That's a point.
No. You didn't check it. You just told me off like during the exam. You told me
Yeah.
I'm gonna tell you like this is wrong. Go do.
You guys actually use this? Oh, okay. 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 Let's get started again. So the whole point here is networks of Markovian queues. The general one I showed you was the Jackson network. I want to, in fact, consider a slight variation on that now. It's called closed Markovian networks. Which is basically a kind of special case of the Jackson networks. Jackson networks, I'll go back here, are often called open queuing networks, but that's too ungenerous, because what he did was he considered open and closed, but usually his networks are referred to as open because there's ways in and ways out. Now, closed queuing networks, you might expect, will be you can't come in and you can't get out. You're trapped. You throw so many customers in there, and they bounce around forever, almost like a pinball machine with no exit. Okay, so let's talk about that. So this is basically due to a couple of researchers called Gordon and Newell. That pair of names is interesting, just as a side point. If you didn't know any better, would those names resonate with you at all? Computer architecture, Alan Newell and Gordon Bell. They're well known for work in computer science, but these are two different people. These are queuing theorists. Okay, I forget their first name, but they're different. So I tried to confuse you, but I didn't succeed. Maybe I did. Okay. Okay. Basically, we're going to put a fixed number of customers in the system. Namely, capital K. Throw K into the system, and they're trapped. They never leave. Basically, they bounce around forever. No new customers are allowed in. So what does that mean? That means that the summation, j equals 1 to n number of nodes, of r sub ij is equal to how much? This is the probability when you leave node I, you go to some other node. If this is less than 1, that difference is probability of leaving. If this is equal to 1, you always stay inside. Okay? And in addition, gamma sub I equals 0, and both of these for all I. Okay. Now, as a result, there's a dependency which Jackson luckily was able to avoid by luck, but now we have a dependency we can't get rid of. There's a dependency among the KIs. I'll call it the state vectors. Namely, this state vector k1, comma, k2, comma, out to kn is such that the summation of the KIs over all i's, over all nodes, is equal to how much? You add a capital K, because they're all stuck there. So this has to be the case. The KIs have to add up to K. That's a dependency, okay? Now let's assume that the discrete state Markov chain we're talking about here let's assume it's irreducible. Go from every node to every other node, etc. That implies there was a unique equilibrium distribution, just like in Jackson's case. That means what we're looking for, as before, is a probability of K1 in node 1, K2 in node 2, out through Kn in node n, that there's a finite number of states. Not true for Jackson. For Jackson, there could be an infinite number. Here, the total sum has to be K. Okay? And how many states are there? What is the number of states? It's equal to the number of ways we can place K customers in n nodes. And what's that equal to? Just a combinatorial n plus k minus 1. Choose n minus 1. Namely, it's the binomial coefficient. Okay, so you can lay those states out. There's a finite number. Matt, next. Inspection, write down the balance equation and try to solve, okay? So I'm going to write that down. I'm going to say the inspection, of course, just to remind you, is simply flow in equals flow out in equilibrium. Flow of what? Flow of probability, okay? And here's the solution, as obtained by Gordon and Newell. It says this probability we're looking for of this joint distribution K1, K2 through Kn is equal to 1 over some constant, I'm going to call it G of the quantity K, times a product over all nodes I equals 1 to n of x sub I, some number x sub I, to the k sub I power, over another function beta sub I of ki. Now I have to tell you what these things are. First of all, by the way, if you look at this, there's a kind of product solution here. It's a product of things that depend only upon the index I. You don't see any ij pairs here. So there's a sense of a product solution here, where g of capital K is equal to an instant constant. It's a sum over all k such that what? The summation of ki as capital K of the product over all I from 1 to n of this function xi, etc. xi to the ki over beta I of ki. In other words, you set the denominator. You add up all this product over all values, and you got to normalize it so the sum goes to 1. That's just normalization constant. Where now including beta sub I of ki is the following. It's one of two things. It's either ki factorial, and that's for the case ki less than or equal to mi, or it's mi factorial times mi to the ki minus mi. And that's for ki greater than or equal to mi. This looks familiar, doesn't it? This was like the MMM case. You keep getting a function growing until you saturate the number of servers, and then it behaves differently. Okay, and the set of xi's it's a set of numbers that solves the following. And that's simply a set of linear equations. It says mu I xi is equal to a sum over all nodes, j equals 1 to n, of mu I xi r sub ij. And that's for all I, 1, 2, up to n. Now, it turns out this looks like, let's say that in paren, it looks like pi equals pi p. It's basically a product solution like that. And I'll tell you what the pi is, what the pi is. With this vector pi is the following. It's mu1 x1, mu2 x2, etc., out through mu n xn. And the elements of p in this similarity are the Rij's. But remember, the Rij's are not state transitions, they are node transitions, but has the same flavor. And of course, we still need the sum of the k's goes to k. So I've not shown you how to get this, but this is a solution that Gordon and Newell came up with. It's a little more complicated, as you can see. Okay, it's this closed Markovian networks. And it turns out that Jackson went further than this. Namely, he noticed that closed networks were a special case of his. What's the special case? When the sum of the Rij's goes to 1 and the gamma i's go to 0. He also allowed the following. First of all, that custom arrival process depends upon the total number in system. Wow. The custom arrival process has always been an independent random variable Poisson process. Here, the custom arrival process depends upon the total number in system. And basically, that essentially creates a closed system. How does it create a closed system as a special case? It generalizes the closed system. How? Remember, gamma I is the external arrival process. He says gamma I can depend upon the number in system. If the number in system reaches capital K, gamma sub I of capital K will be 0 at most K. But he also allows fewer than that. So the closed system became a special case. Second thing he was able to show is that the service rate can depend upon the number of customers in that node. more generally than a multiplicative of mu I times the number ki. So what I'm showing you here is that Jackson was able to show all of these cases, a brilliant piece of work. And you get explicit solutions. True, the closed network's a little more complicated. You got all these things, you got to solve these. But there are the explicit solutions. So we looked at we looked at Burke theorem. The output of an MM1 system is exponential, so you can line them up together. Jackson, an arbitrary closed network, open or closed. And he showed that it behaves as if the departure times were exponential, even though they're not, because you got that nice product solution. Each node behaves as if it's a nice, in Jackson's network, take a node, yank it out, ask, what's the traffic coming in with that lambda equals summation, etc. Figure out what the rate is, assume it's Poisson. Look at the number of servers, basically mu IMI is the rate. Solve that as if it's a standalone MMM size system. Multiply all of those for each node I, and that's the answer for the network. Beautiful. Basically, Gordon and Newell showed you can specialize the case where it's exactly K, but Jackson was able to generalize in the more case I showed you, so we got all those solutions. Okay. There's a little bit more. It's related to these networks, and it's basically something called local balance. And you've basically seen this before, but I want to emphasize it. And this is due largely to Mani Chandi, who looked at these local balance equations. So let me draw our good friend a simple birth-death system as an example. State 0, 1, 2, k minus 1. Oops. K plus 1, etc. Draw the usual picture. And let's assume that we have arbitrary arrival rates. So I got a lambda 0 here, and a lambda 1. These are the generalized birth-death systems. Lambda sub k minus 1, lambda sub k. And the mu's are, again, mu k plus 1 out of k plus 1. Mu sub k, mu2, mu1. Okay. Now let's play Matt's game here. Let's do inspection, okay? But right now, what I want to do is I want to choose a particular set of nodes. And I'm going to choose this set of nodes. Oops, let me make a prettier picture. Let me choose that set of nodes and balance things. For the blue, I'll also do it for this red node. And let's see what happens. Okay, so let's start with the red node. What does the red node say? It says the rate out, lambda k plus mu k, times the amount there, which is pk, is, of course, the amount in from other guys. From below, it's lambda k minus 1. We've done this 1,000 times. Pk minus 1 plus mu k plus 1, pk plus 1. And now for the blue equation, what I'm going to write down, I'm going to balance basically across this cut. That's what it amounts to. What the flow across that cut has to balance. So the rate going up is lambda k minus 1 times pk minus 1. And the rate down is mu k pk. So let's just say that. That says that uk pk equals lambda k minus 1 pk minus 1. That has to be true by balance. Matt told us that. Okay? But I could have done a similar thing with this green cut, the same idea, cut across there. And what equation will that give me? I'm going to write it in blue again, however. This implies that lambda k pk is equal to mu k plus 1 pk plus 1. Basically, the rate out is lambda k pk. The rate in across the green is mu k plus 1 pk plus 1. But notice that these two equations are effectively the green equation. These blue equations that I wrote, by the way, you look at the red. The red is the sum of the blues, isn't it? But more interesting, a piece of the red on the left-hand side equals a piece of the red on the right-hand side, namely this balances that, and this balances that, which is interesting. So piecewise, there's a balance, and that's called local balance, okay? So let me write that down. The blue equations are the local balance equations. And sometimes solving the blue equations is easier than the red equation because they're simpler. So let's say that. Sometimes solving blue is easier than the red. Than solving red. And those are the local balance equations I said. Now it turns out you can apply this to networks of Q's as well. And the point is, if you can show that local balance holds, it doesn't always, in this case it did, you can say, if local balance solves your equations, then it solves the global balance as well. In other words, solve the blues. If you get a solution, you obviously solve the red because you add the two blues and you're going to get the red. This is not true in general. And the converse is not true either. If you solve the red, it doesn't mean the blues hold. But there are networks where you do get the blue equations holding. They're easier to solve. Solve them, you've solved the global. But it's not always true. So the whole idea of local balance is something of importance in networks. So that's what I wanted to say about Markovian networks, if you will. Okay. Big pause. Take a deep breath. We're going to change set of tools now. So what I've taken you through are pure exponential systems with variations like Erlang from single node to multiple nodes. And we got all these beautiful results. Okay, we pretty much know how to solve these things. Next, we're going to go to we're going to go to something called intermediate queuing theory. All of that was baby queuing theory. I sometimes call that, for the book I call it elementary queuing theory. But it's baby queuing theory. It's what you will learn in an operations research course or an introduction to queuing systems. And they'll stop here typically. They'll add Little's result, which applies for more than just exponentials. But they won't go any further because it gets tough. We're going to take tough, okay? So we're now going to go to intermediate queuing theory. And now, basically, we're going to become sophisticated queuing theorists. And in particular, we're going to study MG1, and that's chapter 5. We'll spend a little time on that. Then we're going to go to GMM. And that's chapter 6. Notice that's not quite symmetrical. Chapter 5 is single server. Chapter 6 is multiple server. In this class, have you seen that distinction ever? Of course, the answer is yes, so where? I wouldn't be asking you that if it wasn't true. Have you seen it anywhere in one of our lectures? Yes, we're multiple service for one case and single service for another. Well, I'm going to take you right back here, and I didn't give you a full review back here. We not only did ERM1, we did E sub R M, M if you recall. Nevertheless, even if you don't remember that, let's go and recognize when we get to chapter 6, we're actually going to take the multiple server case. It's a little easy, but let's start with MG1, okay? MG1 is a classic set of queuing systems. So basically, chapter 5, MG1. The famous MG1 system. We're basically going to give up on exponential service. We're letting go of something very precious. But we're holding on to the Poisson arrivals. Poisson arrivals are good for a few reasons. One reason is it allows the mathematics to go through. And the second reason is, as I told you, Poisson occurs often in nature. If you have a bunch of arrival processes, no one of which is Poisson, or exponential interarrival times, and you mix them all and send them in as one stream, renewal theory says if those are independent streams, no matter what their individual distribution is, collectively they look like a Poisson system in the limit of a large number. So nature is giving us Poisson, and sure enough in chapter 5 we're going to keep that. And it will give us a lot of benefits. As we know, Poisson has some rather interesting capabilities. Okay. But basically we're going to be stuck with a non-Markovian stochastic process. Why? What makes MG1 non-Markovian? What made MM Markovian? Remember, the M stood for exponential memory. Yes. Yes, the service time has no memory. No matter how long you've been in service, the time to finish is the same as if you just started. Another way to say that is, all you have to know about the entire past in order to predict the future, as well as any other information of the entire past, is the current state of service and interarrival time. Namely, you don't have to know how long they've been doing it. It's exponential in each case. There's nothing about the past, just know the number system. But now we're giving that up because now we do need to know something about the past. What is it we need to know in MG1? I told you we got an MG1 system running. Here's time t. What do you need to know about the system at time t in order to do the best job possible in predicting the future? You need to know the number and system, and be explicit. The what? No, no. Well, it depends what you define as states. But what do you really have to know? How long you've been in service. That's the thing you need to know. Because how long you've been in service, the conditional distribution beyond that depends upon how long you've been in there. It's not, the tail is not always the same. No one how long you've been there. And we're going to focus on that. That's a rather important observation. Okay? Now, so we're stuck. We don't have the beauty of a pure Markovian system. So, there's many ways to solve this. Okay? We're going to use something called the embedded Markov chain. The method of the embedded Markov chain. Do we know another way to try to solve these systems? Method of stages. The service time can be any Erlangian. We know how to solve that with the method of stages. But we're going to choose any G. We're not going to insist to be Erlangian. That's what we're after. Okay? And the method of stages can get a little sloppy sometimes. You get complicated equations. We're going to find a more direct approach. And when we go to GG systems, namely beyond the MGs and the GMs, we'll find another approach called Lindley's integral equation to be studied when we get a couple of lectures from now. There's many ways. Another way to solve MG1 is something called the method of supplementary variables. I'll describe what that is, but we won't use it. We'll use the method of the embedded Markov chain, which is beautiful. So let's look at MG1. Let's draw the picture. The picture is we have a server here. We have a queue. We have an arrival process. And by the way, are we assuming something else? Yes, we're assuming that it's first come, first serve. Okay. So the arrival rate we know, as always, is lambda. And it turns out to be exponential by definition, which means it's a Poisson arrival process. Okay. That's the M in the MG1. But the service time, single server, that's what the 1 means in MG1. And let's assume it's got some arbitrary service time density called B of x. So you come in from a Poisson process, you may join a queue. When you go into service, you spend an arbitrary amount of time there drawn from B of x, and you leave. And we want to solve for the obvious things, how many people in the system in equilibrium, etc. Okay? So let's write down what we know, therefore. We know that A of t, the interarrival time distribution function, is 1 minus e to the minus lambda t for t greater than or equal to 0. And its density is little a of t. Another thing to comment on, the arrival rate, namely the rate at which customers come in per second, is lambda customers per second. And the average inter-arrival time is how much? The average time between arrivals? 1 over lambda, exactly. If you're never sure where the lambda goes in the numerator or denominator, ask what are the dimensions of lambda. What are the dimensions of lambda customers per second? If you want the average time, you want the seconds per customer, 1 over that. Dimensional analysis is a wonderful engineer's trick and tool. Okay. And while we're at it, the variance of the interarrival time, I'll use A to indicate that it's the A distribution, we know is the square of that. It's 1 over lambda squared for an exponential. We have B of x as the service time distribution. That's the capital P, capital D, capital F probability distribution function. And the little b of x I just notated earlier is the little p, little d, little f probability density function. So if I say PDF, you don't know what I'm talking about. Capital PDF is distribution, little pdf is density. Okay. And the kth moment of service time can be calculated from little b of x as the following. Integral from 0 to infinity of x to the k, b of x dx. That's a definition of the kth moment. Okay. Now, I want a state description. I'm going to get back to your question. I'm pose you again. What is the state description at time t? So at time t, what do I need to tell you about the system right now to give you all the information you need to help predict the future? It's two things. So tell me what they are. The simple one is what? Yes, I'm going to call that's the second thing, but let's write it down. Let me call that the second line. X0 of t is basically the service time already received. By the customer in service. And by the way, if there's nobody in service, how big is x0 of t? 0. He's not received anything, okay? The other thing I need in order to predict the future, go away, is the number in system, right? That's simply the number in system at time t. Okay, now, why do I need to know how long the guy's been in service? I've said it many times.
Because the service distribution is not exponential, so it's not memory.
That's exactly right. If I want to know how long the guy's going to remain in service, if b of x was exponential, namely, looks like that. And if you tell me customer's been in there so many seconds, say t0 seconds, then what does it look like in the future? I've gone through this before with you. It's the tail. And the tail scaled up to have an area of 1. Is exactly the same function. Whereas on the other hand, and I've shown you this many times before, but let's do it again. If b of x was something different, say it looked like this, and I told you the customer had spent, say, t0 seconds in service, what does the future look like for that customer? It looks like, starting here, I'm not going to scale this properly, sorry. It looks like, it looks like this little tail here, scaled up to 1. And the point is, this is different from that. Whereas here with the exponential, this is the same as that. So knowing t0 tells you what the future looks like. You got to know it. In the case of exponential, you don't have to know it. I've said that enough times, but it's important enough to remember what it is. Okay. So this is not a Markovian process. So what do I need? I need a vector. I need the vector number in system at time t and x0 of t, how much service the guy in service already received. That is a Markov process. Because if you give me that, there's nothing else I need to know. And it's, in this case, two-dimensional. We talked about this before. In the dimension of n, it's discrete. Dimension of x0, it's continuous. So somehow we've got a complicated two-dimensional state description. In one case, it's a continuous set of states, time, in service. The other is number in system. And you could try to set up the equation for that and solve it. And this is called the method. Let me say, if you solve this, if we solve this way, it's what I called before. It is called the method of supplementary variables. And you can do it. And it's complicated. But we're going to make a much wonderful observation and say that we can get rid of one of these variables and use something called the method of the embedded Markov chain. I'm going to tell you again I just want to mention it. We want the method of the embedded Markov chain. And basically what we're going to do is we're going to find that at certain points in the time axis, I only have to tell you how many are in the system to allow you to predict the number in the system at others of those points. It's not going to be all points in time. Here's time, for example. If it's a Markov chain, I got to tell you at any point in time, all I need is the number in system, predict the future, but no, I need the time in service. But I am telling you now that there are certain points on this time axis yet to be defined, such that if I simply give you the number in system and not the amount of time in service, that's all I need to know to predict what's happening at these other special points. I'm embedding points in the time axis such that I have a Markov chain for those points. Now this doesn't resonate too much with you yet. You'll see why I'm doing this. But the idea is I want to get rid of how much time is in service. Now if you haven't read chapter 5, can you imagine what those points might be? But if you read chapter 5, please don't spill the beans. And even if you read chapter 5, you seem puzzled, but that's okay. Are there certain points in time when I don't have to tell you how long the guy's been in service? Yes? No, it's not where the exponential intersects the current time. Good try. Yes? Yes. Well, when they just either enter or leave. If somebody leaves service at these points in time, somebody just left here, somebody just left here, at those points, how long has any customer in service had service? 0. Either the server is empty or a brand new person just went in. We know the amount of service there is 0. And if I can solve for the number in system, the equilibrium distribution, number in system, those points, I've got my leg up going. And in fact, those are very, because it turns out that that's enough to give me the distribution over all time. It's a beautiful process. Takács came up with this idea. The mad Hungarian I talked about. Okay, you've seen his picture. Okay. But before we go there, I want to introduce something which affects this idea of looking at how long the guy's been in service. And it's basically something called the paradox of residual service. And it is indeed a paradox. And I'm going to illustrate it to you with an example. Here's a time axis. And suppose we have cars, suppose we're looking at a road, and cars appear at a particular point in the road. First, one car appears here, moves on, another car appears here, another one here, another one here, etc. And suppose there's a hippie. You all know what a hippie is? I'm never sure what the vernacular these days is. Okay, not a homeless, a hippie. Comes along, he's waiting at the road, he randomly arrives there, suddenly out of the blue, and he's going to hitchhike with the first car that comes along. Okay, so let's put the hippie in. Suppose the hippie comes in right there. This is our hippie. And these things are cars. Okay. Now the question is, how long will the hippie have to wait before the next car comes by? Namely, I'm looking for, how big is this? Okay, it's a question mark. And let's assume, because we love it so much, that the cars come around as a Poisson process, okay? Poisson arrival process for cars at a rate, say, lambda, okay? So knowing it's Poisson, how long will the hippie have to wait? How long is that blue piece, okay? Well, there's a few answers, okay? What's the average time between cars? Average time between cars, huh? The average interarrival time, right? So the average time between cars is 1 over lambda. And if the hippie arrives at a random point in time, you might think that he's going to wait half of that, half of 1 over lambda. Okay? But because the car arrivals are memoryless, knowing how long it's been, let me do this in green, knowing how long it's been since the last arrival doesn't affect how long it's going to be till the next arrival. So what does that suggest the blue question mark is? It's running as an exponential. It's the whole exponential. It's 1 over lambda. Well, 1 over lambda does not equal 1 over 2 lambda, okay? And there's other arguments that say, well, it might be 2 over lambda. This is the paradox, okay? So we're going to solve that, okay? And let's use it, let's solve this in general, not Poisson. I want to find the average time of the blue thing, the question mark. Solve for arbitrary interarrival time of cars. Okay? I'm going to call the PDF, the capital PDF, at the time between car arrivals as capital F of x. Namely, specifically, F of x is the probability that tau k minus 1 is less than or equal to x. Well, what's tau k? The car arrivals. So this might be tau k minus 1. That's tau k. This is tau k minus 2, etc. So the distribution of interarrival times for the cars is given by f of x. And its PDF, little PDF, the density, is its density, namely little f of x equals df of x dx. And now, without solving this, because it's going to take a few minutes, I'm going to let you go. It's time. But think about this over the weekend. Or read about it in the book, because it's a very sophisticated idea. And we're going to find, does anybody know what the answer is, by the way? Well, the right answer is, it's 1 over lambda. In fact, the interesting part is, I need another color here now. Let me make green. The interesting part is, and the thing that will satisfy your intuition, is that the interval in which the hippie arrives is not a typical interval. And intuitively you say, well, he's typically going to arrive in a longer interval. And the way to see that is, suppose there were not Poisson arrivals, but the time between cars was either 0 seconds, half the time, or 2 seconds, half the time. Let me just show that. Let's suppose there's an arrival at this point in time. Where's the next arrival going to be? Well, half the time it's 0 seconds, and half the time it's 2 seconds. There may be a bunch of choices of 0 seconds, and here's another 2 seconds. Now, when our little friend the hippie arrives, he's always going to hit one of the longer ones. He can't get there in 0 seconds. So what is the average duration between cars? If the distribution that I just cooked up a distribution that says half the time it's 0 seconds, and half the time, sorry, let me write this way. Half the time it's 2 seconds, and half the time it's 0 seconds. What's the average time between? 1. What's the average duration of the thing that he hits? It's 2. He's going to come in something whose length is 2 for sure. And that makes sense. The longer the interval is, the more likely the guy will arrive in a big one instead of a tiny one. And that's going to bias the blue question mark duration. In the case of Poisson, it turns out the bias is such that this interval in green is 2 over lambda, and this interval here is 1 over lambda for Poisson. And we'll establish all of that on Monday.